Right, so this can be any dimension. So we supposed to have a map. Okay, this can be two-dimensional, can be three-dimensional, and can be even high dimension. Okay. So here's a map. Okay, this is a let me draw the picture here. So this is in Rn, okay, an open set in Rn, and I have a map. Okay, this is a map. We can use I don't like, I prefer use a capital F because this is another single function. Okay, then it's into same dimensional space. Okay, that will be some set, necessary to be open. Okay, inside. Okay, so the target, yeah, the image, you can use let's say tutor, U-tutor. Okay, so this is the image of this map. Now, in the local coordinates, okay, so that can be written like a y1, yn, and f1, x1, xn, and you have an n component, right? Right? So those actually, you have an n functions inside. Okay. Now, then you can find the derivative, right? And you get a Jacobian. The Jacobian of the function is just the matrix of all the partial derivatives, okay? So what I'm going to do is I'm going to write it in the following form. Partial, I'm not going to put the detailed coordinates here, partial derivative, okay? And I put it in this form, okay? And I put them in the vertical form, and I differentiate each term. This is the second derivative with respect to x2 and so on. So the last one is a partial derivative with respect to xn. So you get an n by n matrix, okay? Now we have to label them using y1, y2, yn, x1, x2, xn. If it's a three-dimensional, then just use xy. If it's three-dimensional, xyz. In general, because I don't want to do the two-dimensional case, and the one dimension is only one variable. Okay, so this is a matrix. Okay, now this matrix could be, so for example, if it's R2, right? Using R2, and I have a map from R2 to R2, right? So in this case, my function here, I can use a UV, for example, and here's f xy. I don't need it to xy, x1, x2. Okay, so this could be little f, could be g xy. So this is you don't need to label them. Okay, and then the corresponding then the Jacobian of this one will be f, and here's x, g here's x, partial derivative, and this is y, right? So this is a matrix. So it's 2 by 2 matrix, okay? And then you have a 3, then a UVW. I probably have to use a x2 dot y2 dot, because I use a u2 dot for the image. Okay, it's okay, yeah. So this is how do we define the Jacobian, and it's a 2 by 2 matrix. All right. So the theorem says that if, okay, we assume that the Jacobian of f at the point x0 is invertible. So this is This is a matrix as an invertible matrix. So the determinant of this matrix is not going to be 0. Then roughly speaking, it's a local diffeomorphism. Okay. Then F is I should local. I'm going to describe local diffeomorphism. Okay, it's not. So I have to give a more precise description. All right. So this is a domain. This is U, right? It's in Rn. Here's a point. The map is defined this, and this is another. It's image, right? So this F. And the image here is a Y, yeah, right? And so the image could be very bad. It's not necessarily, here's a domain, but the image itself maybe not necessarily hold the domain. I have to, yeah, I have to say that, okay? So U2 that, okay, U is an open set. Okay? But U2 that, which is the image of U, is not necessary to be open set. It could be one strict line in general, right? Is just a set, a subset. Right? It's not necessary to be open, and F is not necessary to be 1 to 1. Okay, it can send 2 points to 1 point. So it's possible. Looks like that, you know. It's called possible. Looks like that, you know. It's not necessarily open, you know. Maybe here's open, but here it's a 2 strict line there. So, okay, and but the theorem says that if the Jacobian at that particular point is invertible, then of course by continuing, our map is always smooth. Okay, so then in a small neighborhood, it is also invertible. Okay. So what does the theorem says that I can find a smaller open set, okay? Now this can be very terrible, you know, looks like that, the image, okay? Right? It's not necessary, and sometimes the image going back to here. So this looks very bad, but you can find an open set here, okay? I'm going to call it V2. Okay, my notation is slightly different from the book. Okay, so then the conclusion is then there is an open set. Okay, V2 dot at that point. Okay, so such that and another open set V at this point, so I'm going to get a smaller one. Then if the map restrict to F, F restrict to V, okay, is an one-to-one, we call it bijection, is an diffeomorphism. Okay, it's arithmetic. Okay, so the inverse exists. Okay, and it's a diffeomorphism G is V2 dot to V such that F circle, G circle F is going to be the identity map, right? Then both they're invertible to each other, okay? So this is a okay, is an identity. Okay, and F circle G is from V2 dot to V. Tilde is an identity map. Now, what does that mean? That means it's just, you know, you can invert, you can find the inverse of that. Okay, if a V is small enough, what says that? Let's go back to the picture, understand. So you can shrink the neighborhood V around the point. Okay, if you make this small enough, we find out f on this V is a one-to-one and differentiable, and so the image is also an open set. Okay, the image is an open set around the point why not. Okay, and then so you can find the inverse from this V2 dot to V. Okay. So then, in other words, you can find a very sufficient small V so that f restrict on the V is going to be a one-to-one map and differentiable, right? And so the image, so it becomes a diffeomorphism between V and its image, right? So become, yeah, then there's an open set V tilde and another small open set inside U, okay? So that this is a diffeomorphism. Okay, so then therefore you can always find another map from, going back, right? And so the composite of these two are going to be identity map. Okay, so this is a idea. Okay, the statement of the inverse theorem. This is true in a one-dimensional case, right? Remember, it's easy to understand. Remember, we given a function with one variable, right? Here's a special example. Let's understand the theorem. So let f and from an open set to R, right? Be a C infinite, be a smooth function, right? Smooth function, okay? And we also assume that the derivative of C is not going to be zero. It's invertible. Just in this case, just one single function, okay? At some C inside this interval, right? So what does that mean? That means because a smooth function, so that means f prime C, x is not going to be zero for x nearby C, okay? Okay, so the function is always positive, always as a derivative is always positive, always negative. So then it's easy to understand my inverse theorem. So here's a point C, and this is from A to B, right? So the derivative, we assume that as a derivative, we may assume that the derivative is always positive in a small neighborhood. So the graph is increasing for that piece, okay? But it's possible the graph looks like that, somewhere else. But for that piece, as the derivative is always positive, so the graph is increasing. So this is y equals fx. So I can, maybe let's use x naught, okay? So that's the, so this is that's the point. So that is y naught, okay, alpha, okay? So I can find a smaller enough open neighborhood of x naught so that the function is increasing on this neighborhood, right? Okay. So you also have an interval, so you can choose a sufficient small interval containing x naught so that f, there's a, more precise, I'm going to use a spectral number. So there is a small, a positive number, okay, such that f from the restricted to the f is increasing on the interval x naught, right? So you can find so then it's invertible. You can have an inverse, right? Then the inverse exists, okay? So then you can solve. Then we can solve the equation, okay? Over that interval. And we can solve this for x. So x is going to be the inverse function, okay? And you can see that, so that interval is here. It's not necessarily be symmetric about the y naught, okay? So if you have a interval like this, then yeah, this is you get inverse, right? So this is an inverse theorem in a special case, inverse function theorem. Right, so you can solve, and if you want to draw the picture here, so x naught minus shown, x naught plus shown. This is consider this as a map, okay? And this is a interval from C to D, for example, okay? Then it's a 1-to-1, so you can always find the inverse. Okay? Because this we are familiar with the theorem, so inverse means f. Right? For any x in this interval, and you can also switch the order, right? For any y in here, for any x in here. All right, so that is a that is a case, that's a special case in when n equals one dimensional. As long as the function is smooth, so it's the derivative is continuous. If at some point the derivative is not equal to 0, you can assume positive, for example, for simplicity. And then nearby this neighborhood, okay, nearby this, nearby this point, x naught, right, the derivative is always positive. The function, for that small piece, the function is increasing. So you can reverse the procedure, y equals f of x and x equals f, the inverse of f, y, right? Only for that piece, you can even define the inverse function, okay? And forget the rest of that. And this is true for high dimension. This is true for the high dimension case, okay? But it's more variables than involved. More variables than involved, okay? Right. And now we are going to apply this theorem to some problems, okay? Consider a smooth, when we say a smooth function, it means a differentiable, the derivative is also continuous, okay? Smooth function on an interval, on an open set, in, well, let's say R3, okay? Then you let n to be the level set, okay? We can assume that it's just k, okay? So that means here's an open set, okay, in R3, and then this is a level set, right? F equals k. So now I'm going to take a look at a point. So we are using x, y, z, so I have to use a 3 component, okay, at that particular point. We assume that the partial, the gradient of f at that particular point is not going to be 0. Okay. So what I claim that locally, that piece, yeah, I have to draw the picture a little bit better because I want to use much easier to view it as a graph. Okay, so I'm going to draw the surface like that. Okay. So I want to show that locally, that piece, okay, can be viewed as a graph of another function. Okay. So we may assume, for the simplicity, we just assume that because the three components is not going to be all zero. So we, without loss of a generality, we always say that in mathematics, we assume that the partial derivative of f with respect to z is not going to zero. Okay, because there's one, those three components not all equal to zero, and one of them is not going to zero. If this is not zero, what you can get? Well, in a small neighborhood, it is not going to zero, right? Okay. So what I'm going to do is I'm going to construct a map, right? The construct a map, I'm going to use this f. F from still u, that's a u, right? And into R3, okay? And it is defined by x, y, and f of x, y. Okay, so this is a map. Okay, this is a map. Okay. So let's take a look at the map of this Jacobian. Okay, this is from U to R3. So let's look at the Jacobian. By definition, the Jacobian is going to be partial derivative of this vertically, right? So it's going to be 1 with respect to z, and here's f of x. And then differentiate with respect to y, 0, 1, and differentiate with respect to, I have to put the z here for that, yeah. Okay, so you got this. Now clearly, this one, the determinant of this matrix at every point is just the partial derivative of f with respect to z. Okay, so now what? By assumption, okay, by assumption, this is not going to zero. We assume that, right? So this Jacobian at the one particular point, it is not going to be zero. It's invertible. So let's look at the picture here. Forget the detailed formula for the f. So we have a u here, and here's a point, and I have a map f, and into R3. So somewhere, if an image looks like that, it may be very bad. Okay, so I'm going to use x tilde, y tilde, z tilde, and this is u tilde. It's going to be the image of it. Okay. So what I have here is a Jacobian at this particular point is not going to be zero. So that means I can find a small neighborhood, okay? And this even can assume it's a cube actually, doesn't matter. And then if this is a cube, then this does not look like a cube, okay? So it's up to you what you want to talk about, okay? Describe. Okay. Okay. So here, the graph looks like that. The level surfaces looks like that. Okay, this is level surface. Okay, and then there's the image. I don't know the image here. So this is a map. Okay. Yeah. So this is f equals k. So according to by the inverse theorem, right? By the inverse function theorem, I'm going to find a neighborhood u tilde, and I find a smaller one, okay? So that f is invertible, okay? So they are smaller, and when we say small, it's continuous. Smaller open subsets, okay? V contain u, right? And v tilde contain u tilde, okay? So that, okay, the map f u to v tilde is a diffeomorphism. Okay, it's a diffeomorphism. Okay. Okay. Of course, this v contains a point. Okay, And the both, you know, of course, it's contained this V. Okay, contained in V2 da. Okay, so this is an image of F. All right. I can even assume that this is the U2 that I can make it square, you know, because you can always change shrink it a little bit smaller. Okay, so you can assume that this is going to be U2 that one, and Claude make it like a cube. So I'm going to, this is 2-dimensional. Okay, I can assume that this can be any interval. Okay, so small interval around Z02 that, you know, I can have A and B, for example. Okay. Yeah, we can make it like that. Okay. So there is a G, reverse it. Right? There's a G, reverse it. I'm sorry. This should be, I'm talking about V2. Okay, this one. Okay. Maybe let's see, use a different notation. Something like that. Okay. So this is going to be omega. Right. So this is a reversal. And this is inverse. Right. So let's see what we can get. Okay. So right. GF is identity map. So let's see what we get. X, Y, Z, right? And this is supposed to be identity map. And for X, Y, Z in the interval V, okay? In the open domain. So let's see what do we got here. Remember this map by our construction. The first two components is still X, Y, right? The last component, I think is X, Y, Z. Okay. So we have this identity. Yeah, this is identity. Right? Yeah, it's a little bit hard. It's a little bit not easy to see right now. Okay. But anyway, this G exists. So maybe I should express G in the form, because I only see X is always Xn. So we can express. I take a look at another version. Okay. So F circle G. Okay. And X2 dot Y2 dot Z2 dot. Okay. And this is supposed to be X2 dot Y2 dot and Z2 dot, right? Yeah, that's true for X2 dot Y2 dot Z2 dot in this group. Okay. Then in order to remember the definition of this, right? If this component, okay, is A, B, C, right? So my conclusion is A, B, F, A, B, C, right? So that implies A, B must be equal to X2, right? Otherwise, you're not going to X2. So that implies G, X2, Y2, Z2, as can be in the form also like that, okay? And I'm going to put the G, X2, Y2, Z2, can be expressed in this form. Okay, let's conclude this inverse function, inverse map, must be in this form. You can see that from here even. Yeah, you can replace this by by W, then Z depends on X, Y, Z W. Okay. So anyway, so you have this, you have this map. Okay. Then I think we find we already find the function we need. Right. We already find the function we need. Okay. Yeah, let's go back to here. So this is yeah, let's the picture. Yeah, difficult, complicated here, the picture. Okay, so when you construct the F, right, this point, okay, and the Z, actually the Z 0 is actually is going to be F is going to be K, right? Because our construction F, the third component is it. So it's actually it's going to be K, right? And so I want to take a look at from here I can tell I just fix the fix that point. Okay. So let's see what do we get here. Yeah, I'm going to let this. This is in general true for x in the interval. In V tilde, which is omega pi, right? And in particular, when I choose K, okay, then okay. All right. Yeah, I probably have to go back to this formula, okay? So you can tell that maybe use x, y, you know, this x2 that equals x, y2 that equals y, okay? So so you can yeah, so you can see that if I put the f again, okay? I want to see what I can get for any other, okay? G, x, y, theta, and k, okay? So that is going to be the inverse. Okay. Right? And so that indicates, okay, so on the other hand, this is going to be x2 dot y2 dot f x fx I'm not this is not G2, I just put a G there, right? So it's not G2. I'm trying to show you here. This is by definition of F, and this will be G. Okay, so they are always equal to K. They are always equal to K. Okay, so what does that mean? Okay, they're always equal to K. Okay. That means if I'll keep writing G2, that's good, okay. So that means, yeah, I'm trying to, so I let H to be X, Y, G, X, Y, K, okay. Then you have X, Y, H is always equal to K. So in other words, this level surface passing through this through point is going to be described by the graph z equals h of x. Okay. So this level surface locally in that small neighborhood is described by as a can be described by as a graph of this function h. Okay. So how do you construct this function? We use the inverse theorem. Yeah, use the inverse theorem. Yeah, let's go back a little bit. It's notation. It's very bad. Okay, so the idea is that you find the inverse function, then you have a 3 component. Okay. Then you because this is the identity map, so you end up with yeah, you can get a function g here in general. Okay, but I use this g to construct the h. Okay, yeah, construct this h. And because this will send the map, this G actually, the image of this point actually gives us a graph. Okay, so this is G. So on the picture, it says that on the picture here, when the third component is Z. So actually, I was talking about. Yeah. So actually, what I was talking about is this plane. This plane is actually the image of this level surface. Okay. That's it. And then using that, you can construct a function so that the graph of that function is this level surface. All right, so that's it. And so what the theorem says that if you have a level surface, okay, F equals K, and at the arbitrary point, okay, if one of the gradient of F, right, is going to be the 3 functions here. Okay, at the point this. If this is not going to be 0, one of them is not there. So in case if this is not 0, that means roughly speaking, you can solve through x in terms of z. So when we can solve this equation, right? Okay, for x. So in other words, locally, okay, so x is going to be a function for yz. So that means it's hyz such that, okay, so you can get solution, okay. So that can be, that's for yz close to that, okay, you can get a solution, okay, and that's much easier to understand. So as long as the partial derivative of f with respect to x is not equal to 0 at that particular point, then you can get, so sometimes you get two solutions, but you have to choose one close to, you have to make sure x is close to x naught, okay, okay, such that, okay, you know, you choose that piece, okay. Well, let's take a look at examples. Sometimes we can solve it, okay, example, okay, and right, so here's fxyz, okay, we get xq, you know, minus xy plus yz, for example, right? We want to understand this surface, okay? And so the gradient of f, you get 3x squared minus y, okay? Partial derivative, and then derivative y with respect to x, and the derivative f with respect to z, right? So 3x squared minus y, and you differentiate with respect to x. Then you differentiate with respect to y, negative x plus z, and this. Okay, in general, you know, we want to make sure this is not going to 0. So if, okay, at point, okay, at let's assume that's 1, 1, 1. I can make it easier. 1, 2, 3, doesn't matter. Just take a look at the point. Okay, so that's going to be 2, right? That's a 0. Okay, when x is 1, y is 1, just 2, and that is a 1. Okay, so based on our theorem, we can, the first component is not 0. The second component is not 0. We can, by the above theorem, right? We can solve this equation. And that equation, the value is going to be 1, well, actually 1, okay? Yeah. When x equals 1, y equals z equals 1, that value is 0. Okay. For x, in terms of yz, we can also solve it. We can also solve this one for z, because the partial derivative of z, right? And which we can do, you know, let's see, in terms of x, y. Let's try, okay? All right, let's go back to the equation, okay? Let's go back to the equation. You know, sometimes it's guaranteed, does not mean you can express it in terms of x, okay? xq minus xy plus yz, okay, equals 1. Unfortunately, okay, this is a polynomial of degree 3, okay? So we cannot express x in terms of yz explicitly, okay? Now we can, okay? Okay, so we cannot, but there's a theorem guarantee we cannot express x in terms of y and z, okay, explicitly. Okay, just because it's polynomial degree 3, I don't have a formula. Okay, second, I still look at this. Okay, I can solve for z. Z is easy. Oh, z is going to be, right? 1 minus x cubed plus xy divided by y. Okay, so you do get solutions, right? And that is my hxy. Okay, yeah, you can take a look at when x is 1, y is 1, I get 1 minus 1 cubed plus 1 divided by 1. So the answer is 1. Okay. And this is so the surface can be viewed as a graph of a function defined the locally, right? So locally, the level surface, okay, nearby that point in the space can be viewed as a graph of h. So h is going to be this, right? On an open set, on a domain, okay, containing the point x and when, which is in xy plane. Okay, so it's clear, right? But you cannot view the whole level surface as a graph of some function. It sometimes may be impossible. For example, when y is 0, okay, when y is 0, x, yeah, you cannot view the whole level surface. That's a regular surface, but you cannot view the whole level surface. How about this point, right? How about this point? Yeah, this level surface when y is 0, right? Then you cannot view when y is 0. Let's take a look at this again, right? X cubed minus xy plus yz equals 0, right? So when y is 0, yeah, at the point, let's take a look at the point. So when y is 0, x is 0. That's too bad, right? And this is going to be 1. No, x not. Okay, this is the equation. Okay, when y is 0, at the point, let's say when y is 0, x is going to be, z can be any value, right? Z can be any value, x is going to be 1. Right, z can be any value. Z can be, let's say, just say 1 or 2, doesn't matter, okay? Just take a look at the picture, okay? So this level, let's take a look at the gradient, right? The gradient, I forgot the formula. The gradient is 3x squared minus y and the negative x plus z, and that is the y, right? When x equals, yeah, when x, yeah. So at the point, and when x equals 1, y 0, that's 2 already, great. And when x equals negative 1, z is 2, so it's 1. Yeah, let me double check if this is a point on the graph or not. Yes. So when y is 0. Okay, so this is a point. Okay. So the y is 0, right? Clear. So locally, this is not going to be 0. So locally, the level surface is a regular surface at that particular point. The questions cannot be viewed as a graph of a function defined on the xy plane. Okay. So the level surface, okay, nearby is this point. Nearby is this point. Okay, is a regular surface. Okay, but cannot be viewed as a graph of something like that. Okay. Okay. And why? The reason is I cannot solve for the third component 0. I cannot solve for z in terms of x. in terms of x, y. Okay, I can get h, but h is not defined when y is 0. Okay, when the y is 0 at that particular point. So what I can do based on this information, I cannot solve for x because you get a cube. So I can solve for y, okay? Because partial derivative of y and yeah, 1, 0, 2 is going to be 1, which is not going to be 0. Great. So we can solve this equation f equals 1 for y. So let's try. So what is f? X cubed minus xy plus yz equals 1, right? And that's okay. That's obvious, you know, this is a linear, right? So y is going to be, right, negative xy plus yz. This is the element function, okay? So I solve for y, so y is going to be 1 minus x cubed and z minus x. Great. So this is a defined when at the point when x is y is 0. When x is 1, z equals 2. Okay, so this function h xz. Okay. So so 0 equals h when x is 1, z is 2. Okay, and this is defined. Okay. So that means locally nearby that point. So that means the level surface. Okay. Nearby that point. What is the point? The point is 1, 0, 2. Okay. Can be viewed as a graph, okay, of y equals h. Okay. Then, so anyway, I'm not sure this whole level surface is regular surface. I haven't checked every point, but nearby that point, it's a regular surface. Okay, and it's a graph of a function. Yeah, it's a graph of the function. Okay. Yeah, it's harder to draw it, you know. It's harder to tell when this is not equal to 0 because you cannot solve for x. You cannot solve for this equation. And how can I say, if x, y, z satisfies the equation, can you show that the derivatives not all equal to 0? Okay. Yeah, my question is question. Okay. Is this level surface determined by, is this a regular surface? Okay. That means you have to show that if x, y, z satisfies this equation, you have to make sure that the gradient is not going to be 0. So gradient at every point is going to be 3x squared. We only checked a couple points here, right? Minus when I differentiate x, that's right? When I differentiate y, I get a negative x plus z, and when I differentiate z, I get a y. Yeah, don't forget the negative y, yeah. So maybe I made mistakes above when I differentiate. Yeah, let's go back. People forgetting, this is a derivative. Oh yeah, it's here, negative y, okay, so I'm fine. So this is a multivariable calculus problem, right? So the question is, do we, is it possible all the components are 0? Any point, let's find a singular point on this level surface, right? Maybe we can find it, right? Yeah, let's look at those 3 equations. Can we find how about they're all equal to 0? Okay, when yeah, when they're all equal to 0. Okay, let's solve it. If not, that means if a point on this, then one of the other three equations is not necessary. It does not hold. Okay. Okay. So singular point. In order to find singular, you have to find out any point on the level surface gradient of f. A point on the level surface satisfies first equation. Then the gradient of f is 0. Let's see whether it's possible or not. So when y is 0, that's equation 1, equation 2, equation 3, equation 4. If y equals 0, okay, by equation 4, y is 0. Then by equation 2, x is given 0. Okay, and then by equation 3, z is given 0, x, y, 0. But when does not hold in this case. Okay, does not hold for x, y, z equals 0 and 0 and 0. So that implies the level surface is a regular surface. Okay, but maybe somewhere, you know, this cannot be viewed as a graph of z equals h of x, y. But you can always solve for y, you know, or z or x in terms of other two variables. Okay, so it's guaranteed it's a regular surface, but not necessarily to be the graph of the whole one single function. Okay. So this is about the application for you know, the universal theorem. It's guaranteed you can always locally, okay, if the gradient of f is not going to 0, locally can be viewed as a graph of some function. Okay. Okay. So let me state what we have here. So if f x not finite, okay, is going to be k, and the gradient of f is not going to be 0, okay, then the level surface, okay, the level surface of f nearby that point, okay, can be viewed as a graph of some function. Okay, it depends on the problem. Okay, as a graph of some function. These are, you know, these are z equals h x y, or y equals h x z, or x equals h of y z. Depends on the partial derivative of the original function at that point. Okay, either you can solve for z or solve for y, solve for x. Okay, that's the statement. Another theorem I want to briefly mention is as follows. Okay, if you have a map from the surface to another surface, and here's a point, send the P2 dot f of p, right? Okay, so then you have a induced linear map. Okay, this is this from tangent plane to the tangent plane. Okay, as a linear map, you can talk about linear map as singular or non-singular. Okay, linear map is linear algebra. You know, from that was from 2 dimensional vector space to another 2 dimensional vector space. So the theorem says that if DFP, is invertible, okay, in other words, as a linear map, it's easy to check, invertible. Okay. So in other words, the matrix, the corresponding matrix is non-singular. Okay. You can find the matrix. Okay. For example, if you choose a basis E1, E2, E1 tilde, E2 tilde, then DFP, okay, E1 tilde, E2 tilde is going to be here's a matrix A. Okay, you can, okay, that means determinant of A is not going to be 0. Okay, this can be characterized by the matrix. You know, every abstract linear map can be expressed as a matrix. Okay, then F is a local diffeomorphism between the two surfaces at the point P. Okay, what does that mean? Okay, let me draw the picture here. So this is a surface. Here's another surface. S tilde. This is the point P. This is point P tilde. Okay, it's image of F. So so that means I can find a small open set V. I can find another small open set V tilde. Okay. In other words, there exists open sets V S. Okay, and V tilde S tilde, such that, okay, of course they're containing the point P, right? So otherwise, okay, and F from V to V tilde is a diffeomorphism. Is a one-to-one bijection. Okay, it's called bijection. It's differentiable by bijection, so it's one-to-one. It's on two, you know. Okay, yeah. Sometimes they just say by. If you don't want to talk about differentiability, it's called bijection. It's just one. Okay, it's not that globally is not true. Okay, only small neighborhood. Okay, so this map, when you restrict it to a small, okay, but this is easy to understand, because a surface, we can always convert a surface to you can view the surface using an open set in R2. Okay, so the proof is very simple. I just give a sketch of proof. I don't want to go for very technical formulas. Otherwise, get lost easily. Okay, so here's a surface. Okay, this is a map again. Okay, here's a point. Here's P tilde. So when we are trying to understand surface, what we do is we find an open set. Okay, here U and V, right? So this is a part. Okay. And let's color it. This yellow part comes from here. Okay. So basically, we translate the problem into a problem for a map between two open sets in R2. Okay. So here's another picture. U tilde, V tilde. And this is a, okay. And here's another one. Okay. So this is a map, sigma. This is coordinate, right? So here's another one. Right, we cover that. So this will be U tilde, V tilde. Okay, this is a map sigma tilde. Okay. So now let's take a look at the picture. Okay, F is send the whole surface to onto not onto into another surface. This is S. This is S2. So at least send the yellow part somewhere here. Send this yellow part cover this neighborhood. So this is a yellow part, right? Okay. I can always assume that the image of I can shrink this yellow part so that the image by the continuity, right? Image is containing the yellow part, okay, as a green part. So we can assume that we can shrink. This is a surface V, right? So that's a V2, okay? We can shrink V, okay, such that this is a V. Yeah, well, we haven't. Yeah, first of all, we're looking for a V, right? So that the F becomes a diffeomorphism. But right now, you take an arbitrary V, which is the image of the surface patch, okay? But we can shrink the V such that this V is contained in this yellow, this green one, okay? So yeah, make it simpler. So such that okay, that's a V tilde such that the V tilde such that F V is contained V tilde. Okay. All right. So now we don't worry about this, right? So now I have a map from I can pull back. So actually I can have a map F. Let's see what the one on the top is F. The one at the bottom I can use. Should I use the same letter? Use the X, Y, Z. I can use H. Okay, I can use H. Okay. But no, coming from F, so let's still use that. So what we get here is actually you can F, okay? So this is UV, right? Take arbitrary point UV here, and then you go to the surface, and you send it to the image here. Then there should be another map. Okay, so somewhere here. Yeah, because sigma is a one-to-one map. So some point here, we can always find that number. Okay. So yeah. Okay. In other words, this is a point F circle UV somewhere here. Then the corresponding U2 V2 yeah, that's U2 V2. Okay. So send it to this point. Therefore, so U2 V2 equals F2 UV. Okay. And how that determines U2 V2? Well, if the image is going to be that point. Okay. So so you have this identity. Okay. Now the point, the conclusion is DFP is invertible. Okay. If and only if F2 okay, the Jacobian of F2 at this point is invertible. Okay, you can find you can write down the detailed formula for the linear map, D capital DFP, and you find out the Jacobian is involved. Okay, once the Jacobian is not is invertible, then you apply the implicit function there. You can find a smaller neighborhood. Smaller neighborhood here and small neighborhood here, so that you can find the inverse. Okay, so that means this implies there is a small neighborhood U tilde containing, okay, and U, not U2, okay, okay, and okay, such that F2 dot restrict U is a differomorphism. Okay, so that is F unique. Okay, then this implies F on this sigma U2 sigma U2 dot is a differomorphism. And this is the idea. Okay, so the idea is that you just translate the abstract map to a map on R2. Okay, then if you on R2, you can the linear map is invertible, means the Jacobian is invertible. Okay, so this is look at the picture again here. So I'm going to get here and get this. I want to find a differomorphism, right? So I want to find a smaller neighborhood. So F restrict to this neighborhood is a differomorphism. What I'm going to do is I translate everything into a map from open domain to open domain in R2. Then you can compute the Jacobian. Okay? If Jacobian is not going to 0, then this is it. Okay? Then you get you can find the inverse function, the inverse map for this F2 dot. If F2 dot is invertible, then F is invertible. Okay, so the idea is I translate everything on the surface to something on the domain. Okay, and so you can solve the problem because we can use calculus to differential functions, okay, in the domain, in Euclidean space. We cannot work on the curved space. Okay, we can only work on the flat surface. Yeah, so we translate everything on the curved space to a flat space and work on that. Okay, so that is the idea. I sketched the idea, Okay. In the book, everything is no picture here, just the equations, words, and all right. So that's it for today's class. What should we enjoy?